This has to be the hardest earned 20 circles I have drawn in a long time. So this is an update for section 2.6. It is basically a double update, but because I have been ahead with my reading and my work by a couple of weeks at this time of the year, December, mid-December. Today is December 15, I think, or 16. It's a Monday, and I'm off work. And so I've been able to get ahead in December, and I'm going to get behind later on in 2025 as I get towards the summer, take summer breaks. But yeah, this is a double update. It took a long time. 16 proofs, many of which I'll show you. I don't believe I've really nailed them completely. And 20 problems. So I'm at 273 problems, of which 181 are proofs. It was all dual spaces, and I actually started by working through the early problems of Freidberg in suspense, FIS. But yeah, this section has been almost like a fractal. You know, I've gone in and in and in, and there's more that I could do. There's some dual spaces reading that I can do in Hoffman and Kuhn's and Axler, but I'm going to wait for when I do it with Axler and keep going. Incredibly enough, I already have dumped a considerable amount of time into this section. So it's all about linear functionals, where you take, it's a function that takes everything in your vector space and calculates it into a single number in F. That's really what it is. It's a linear functional. F, GH, you know, these are the types of letters that are used. So for example, an integral is a functional. And this is an example of one. Of course, when you define the dual space over the vector space of all linear transformations from B to F, denoted by V star, they have the same dimension. So when you do the duals, they have the same dimension for those duals. If you, of course, you have V to W, W may have a different dimension than V, but W star and W are going to have the same dimension. There's all kinds of algebra that you can do with them, and this theorem is very important. The transpose of the transform goes back. So you're going V to W, then you're going back W star to V star. So W dual to V dual. And you have this G function that you use. Some examples. And then, of course, the double dual. And the double dual sets up a correspondence between x and the x hat, which is a function which is the result. So it's basically, the dual is basically a linear functional of a linear functional. By the way, it's explained in Helmholtz better than in FIS. Incredibly enough, Helmholtz usually very cryptic with the terminology, but boy was I really helped by reading Helmholtz for this section. And yes, I looked into the other two books, and there's more, but I was like, no, I'm going to do it in Axler and polish it off then. Very difficult problems. So let me just go through, and the pace was very slow because I got stuck in a couple of problems, but I decided that I wanted to solve them without looking at the answer. That is, I wanted to make sure that it was correct when I looked at the answer, before I looked at the answer. And it was problem 5. Before that I did problem 4, which was similar, and I felt really good about that, even though I did spend a considerable amount of time. I worked out the example. This is not worked out in the example. You have to figure it out yourself. So I did. But it's tricky. It is tricky. Did okay in the true and false. Did okay in the problem 2. I mean, got them all. Got all the 3A. So it's all about how what the functional equation looks like, and then you can evaluate it. In some cases. When I got to number 4, boy, did I try different things. I just went in many different wrong directions until finally I realized what the correct answer was. There are pages and pages of scratch in here that I threw away. But yeah, I did figure it out. And then I figured out number 5 before looking at the answer. Number 7, which is in the answers, I came close. I was very close to getting everything right. I got almost everything right. Feel really good about it. And then I stopped, and then I went into Halmos. And so Halmos has a section on dual spaces and a section on reflexivity, where all these theorems that are required to understand the problems are explained. The concept of annihilators is fully fleshed out. I believe this is a mistake in FIS. FIS should have had a section or a chunk of text going into details of what an annihilator is, and of course Halmos does a much better job by actually explaining it. And the same is true with Hoffman and Kuntz and Axler, but I just did not want to spend 4 weeks in what I think should have been a week, and I already spent 2 weeks on. This is all reading from Halmos, which I just showed you. With then some comparisons with FIS. I went back because FIS uses different terminology. And it's all about this thing of where you go with the annihilator. The annihilator goes into the other space. So if what you're mapping to the annihilator has the dimension m as a subspace of n, then the other part has n minus n as a dimension. So the annihilator of m, being m0, has dimension n minus m, not m, because it maps to the other. It really maps to the quotient space. Really, it's a lot like a quotient space. So I kept drawing these diagrams as I was working out the problems. I got confused because I felt that the way the problem is laid out, it looks like it should have been a typo. I didn't understand. It didn't make sense to me that it was m, that it was n. Threw me for a little bit of a spin. I said, I attempted it. Don't know. But every single one of these problems was a hard battle to figure out, because the annihilator is always sending you somewhere else. Now in this case, I did get it. I did understand what I needed to do, but the answer uses the operators, whereas I just did substitutions, so I only gave myself half a credit. Then problem 12, I think I got right. 13 was all right. 14 was all right. Then when I got to 15, yeah, I gave it my all. And I do see how they're the same sets, and that's why they're equal. I do see it, but I didn't feel like I laid it out really well. Then problem 16, I did a proof that I think is reasonable, but I had a lot of back and forth of trying to figure out what I was doing. I'm not sure it's correct. The same for 17, the same for 18, the same for 19, and then I think 20 is all right, but there's just a lot to go through, and in some cases I just didn't feel like I made the right connection between the dual spaces and the source spaces. Didn't feel like I made the right connection in some cases, but I did give it my all. This section was a bear.